difficulties, and do we have sound online now? Oh, good. All right. If you're online, all you just missed was a bunch of names. What did I miss? Oh, how is everybody doing tonight? Folks, that was pretty weak sauce. How is everybody doing tonight? All right. You see, we gotta overcompensate because we don't have a full room tonight. So we're doing our best. Thank you for toughing out this crappy weather and joining us. I know we don't have a lot of first timers, but and now this stopped working. Great. Just tap it once. Sometimes it does that. Okay. What is Astronomy on Tap? Well, it's a worldwide phenomenon. We have locations across the globe. The first one was in Brooklyn, New York, now almost 15 years ago, actually. Our own location has been here since 2017, so we're going on 9 years now. So we're very happy about that. And I know that the burning question is, what makes us different from the rest? What makes us so special? Well, we're interesting. We have, besides all of these interesting technical difficulties, we have interesting speakers, and we have two great ones tonight with great talks. We are interactive because y'all will get the chance to ask questions of our speakers by texting our line here, and then I'll come up after their talk and ask the questions. So please take advantage of that to the fullest. And lastly, we like to have fun. As you all know, we will end off with our trivia tonight, and we have some really actually cool prizes because since one of our talks tonight is about exoplanets, we have all of these famous exoplanet posters that, thank you, Erica. Or should I say Vanna? You know Vanna White? No. Oh. That are concepts of they're like travel posters, right, that you'd see at an airport, so concept art of exoplanets. So they're really cool, so stick around for trivia if you want a chance to win. Yes, tonight's agenda. Aaron?
Hello. Tonight's agenda. First, we have recently minted Dr. Dinesh Veypatty Radhakrishnan talking about tracing the solar wind's journey into Earth's magnetosphere. And then we'll have the Astronomy in the News. Caleb is back on scene doing the Astronomy in the News. And then we're going to have UTSA PhD student Cindy Liu talking about Sub-Neptune exoplanets from magma oceans to water worlds. And then our good old-fashioned trivia produced by Sam. So we'll see what we're in for tonight with that. And then I'll introduce Dinesh. All right, first talk of the night, we have Dinesh, Dr. Dinesh Veypatty Radhakrishnan. Let me get the... Dinesh recently defended his PhD in space physics at the University of Texas at San Antonio. He has a robust academic background with a Bachelor of Engineering in Electronics and Communication and a Master of Science in Physics from the Birla Institute of Technology and Science, Hyderabad. His research focuses on Kelvin-Helmholtz instabilities at Earth's magnetopause, funded by the NASA Finest Grant, which is a prestigious prize in our realm. His past experience includes modeling lightning activity in Venusian cloud systems and developing lightning detectors. And today we're talking about the magnetosphere. Dinesh, well, for the moment, you're going to be over here. So take it away. There was one new timer. For the uninitiated, we have a drinking word, which means when you hear the word uttered, you drink. Dinesh, what is your drinking word?
Since it's finals week, I don't want you guys to get drunk. I'll stick with magnetic fields. Yeah. All right. So today I want to talk about how, solar wind, all these energetic particles emitted from the sun, make a way into Earth's near space plasma environment called the magnetosphere. And I want to give this talk in the context of the recent Veterans Day storm. Hopefully that's still fresh on your minds. So just a few terminologies I'll keep using throughout this talk is, uh, first is solar wind. So our sun, it continuously emits streams of high speed, high energetic particles called the solar wind. We don't really have to worry about this too much because our Earth's magnetic fields, it acts as a shield and kind of deflects almost all the solar wind that comes our way. Uh, Even though the solar wind is deflected, it can still make its way into our Earth's plasma environment, and that's what today's talk is going to be about. This region of space where this deflected solar wind flows, that's called the magnetosheath. One thing you need to know about space plasmas is that when plasmas flow, it also drags the magnetic field along with it. Like, so over here, when in your atmosphere, when neutral winds flow, they don't really have any impact on the Earth's intrinsic magnetic fields. But that's not really the case in space. When they flow, they are also going to drag all these magnetic fields along with it. All right, I regret choosing that word. So when it comes to Earth, Earth's magnetic fields are kind of fixed. They really, it really does not change its orientation too much over time. Whereas that's not the case when it comes to magnetic fields from the sun that fills up the interplanetary space. These magnetic fields from the sun, we are going to call it IMF in short. It stands for Interplanetary Magnetic Field. All right. So, in your interplanetary space, your IMF does not have a constant orientation. It's going to keep on changing over time. And this is an example of all the different possible IMF orientations that we typically see in the interplanetary space. The most common one is the Parker spiral IMF orientation, where almost all of the magnetic field is in this is in the ecliptic plane on which the Earth is orbiting around the sun. But today's talk, we are going to focus more on northward and southward IMF orientations because they are particularly interesting and they drive a lot of dynamics in our local plasma environment. So recently, on the Veterans Day week, we had two major solar flares emitted from the sun. The first one was quite weak, but followed by that, we had another stronger flare. So around midday of 10th of November and midday of 11th of November, these flares were emitted. When these flares are emitted, they don't, it takes a couple of days for them to reach all the way to Earth. So the effect of these flares was observed on November 12th and November 13th. On November 12th, as you can see, your solar wind, which had a pretty low speed, had a sudden enhancement in both your velocity and density, indicating that these flares have reached quite near Earth. And on this day, we were actually able to see auroras all the way down in San Antonio too. And I've seen reports of people seeing it with their phone cameras all the way in Mexico. So this was a very strong flare. And I hope, because the following flare, which happened the next day, it packed a bigger punch. Like, it's flowing at much higher velocity. It's going almost about thousands of kilometers per second. And we hope, because we saw yesterday, probably we are going to see the next day too. And we drove all the way down to Bernie to check out this flare. But on this day, even though it had a bigger punch, we were not able to see as strong of an effect on that day. So why is that? The culprit almost always comes down to what is the magnetic field orientation when it's struck. So when we look at the magnetic field data, it is unfortunately not available yet. So I tried to go and plot this with their online data. It's just a month old and we don't have this data product available as of yet. But because I'm a space physicist, I can kind of guess that on the 12th of November, your magnetic fields, the Z component of the magnetic fields was pointing southward, whereas on the next day, it was pointing northward. So because, I'm something of scientist myself, I can kind of guess all these things going on. Yeah, so I'm just joking. We do have other data products called, which kind of give us real time information on these solar wind parameters. And I was kind of monitoring these parameters on that day. And as you can see over here in the first plot, which is how your magnetic field changes with time. And this was on the 1st of December when I was making these slides. So you see that your magnetic field BZ, which is the red dot, kind of goes positive and negative and so on. So it keeps on changing its orientation with time. So on that day when I was monitoring this real-time data product, I could see that, on the first day, even though it had lesser punch, your magnetic field orientation was good enough was southward, and the next day it was northward. So what goes on during southward IMF? A very fascinating process called magnetic reconnection. So, your plasmas, as they move, they are going to drag the magnetic field lines along with it. And when two plasmas flowing towards each other, which have embedded magnetic fields within them, and they are kind of pointed in the opposite directions, then at the point where they kind of interact with each other, there's a topological change of these magnetic field orientations. So within this small region of space called the diffusion regions, the topology of these field lines change, and as a result, most of the magnetic energy which is stored within these field lines gets converted into kinetic energy of the particles. So a very simple way to think about this is like the magnetic fields kind of act as a slingshot and accelerate all the particles, all the plasma particles on either side of these plasma regions. So this is the context of magnetosphere. So this region of space where the deflected solar wind is flowing. So over there, your magnet, it's going to be flowing along radially in this direction, and when it interacts with Earth's intrinsic magnetic field, which is pointing northward, when these southward pointed field lines interact with these northward pointed field lines, they reconnect at this point of space called the X line. And it's going to act as a slingshot and accelerate all these particles along these magnetic field lines. And these particles, these energetic particles, they are going to be, flowing along these field lines and then impact our Earth's neutral atmosphere. So depending on the energy levels of these electrons and ions, they can ionize the neutral molecules in your atmosphere, and the recombination process emits light at different frequencies. And these are the different typical frequencies of auroral emission lines that we usually observe. So when it goes down to further lower latitudes, we see red to be more dominant because extremely high energetic particles are the only ones that can make their way all the way down to such low latitudes like how we are in Texas. Another interesting thing that happens during the magnetic reconnection process is the formation. Okay, sorry. So a formation of a boundary layer which further separates your magnetosheath where this deflected solar wind flows and magnetosphere where Earth's pristine plasma environment is. So your magnetosheath It's kind of cold and it's very fast moving, and it lies on magnetic fields of the sun. Whereas your magnetospheric particles, they are much hotter. They are about 50 times hotter, and they are pretty much slow moving. So these are very two distinct plasma populations, and reconnection kind of mixes up these plasma populations to create a region of space with that has intermediate properties between both of them. And as your plasma flows, this intermediate region convects down the flanks, and it forms a very thick boundary layer which further separates your magnetosheath and your magnetosphere. This boundary layer is pretty much formed every time magnetic reconnection takes place. All right, so these are the key processes that happen during southward IMF scenario, and because during southward scenarios, day-side reconnection, it's very ideal for particles to get accelerated along those field lines to bombard Earth's neutral atmosphere. You see a much bigger impact going on. During northward cases, reconnection is still expected, but because in the day side, both the IMF orientation and Earth's field lines orientation are parallel to each other, we don't expect reconnection to be operating over here. They kind of shift towards the poles where again, or shift towards the poles because over here, your field lines are going from north to south. It's southward oriented, and these northward oriented field lines can interact with them over here, and reconnection can still operate. You can still expect some amount of energetic electrons and ions to flow into your neutral atmosphere, and your boundary layer still forms. So reconnection kind of operates at any given time for any given IMF orientation. It's just that the location where it operates keeps changing depending on its orientation. But the highlight is during northward cases, another interesting phenomena called Kelvin-Helmholtz instabilities kind of operate. So to understand this, like I need you to think about the day you went to the beach. It's a nice sunny day, the wind is coming at you at a very high speed, and the ocean water at a relatively slower speed. So this difference in speed is one of the reasons why we have waves in the ocean. And similarly, this deflected solar wind, it's very fast flowing, whereas the particles in your magnetosphere are very slow moving. As a result, waves form at this boundary separating these two interfaces, and these waves can kind of roll up and form these extremely large scale vortices that you see over here. These vortices again mix the solar wind and particles of your magnetosphere, and in this way, some of the deflected solar wind make their way into Earth's near space plasma environment. So over here, I have a simulation of what happens when you have plasma flowing along the y direction, and you just perturb this boundary a little bit, and you see that once these boundaries perturb just a little bit, then you see these wave-like instabilities kind of roll up, and lead into a very turbulent end stage process. So this kind of phenomena is what we expect to be happening even in space too, and it does take place. And these vortices are pretty large. They can grow as large as 25 times the size of Earth. There's nothing that really stops them from growing. So you have a northward IMF case, and for this case, reconnection happens, and then you have this low latitude boundary layer formed, and your vortices start developing at this boundary layer. But over here, if you really think about the field line geometry, your plasma is flowing along x direction, whereas your magnetic fields are pointing up to down. Your plasma is flowing in this plane, and your magnetic fields are pointing up and down. So it's like your flow is perpendicular to the magnetic field orientation, and this is like the best possible scenario for formation of KHIs because they don't really have any sort of magnetic stabilization to overcome. So it's very easy for them to form these vortices, and these vortices grow extremely large and can transport all of these plasma flowing in the magnetosheath into your magnetosphere. So this region, it specifically goes into a region called your central plasma sheet. And we know that for northward IMF cases, the central plasma sheet turns out to be extremely thick, cold, and dense because, well, a large amount of plasma population is getting a large amount of these deflected solar wind makes its way into your magnetosphere. What about other IMF orientations? Reconnection is still going to take place somewhere. It's going to form these boundary layers. And once these boundary layers are formed, there is a scenario where you kind of have some amount of magnetic field in the direction of flow of these plasma in the magnetosheath. So because there is extra magnetic field present parallel to the flow, uh, these KHIs have kind of like an additional hurdle in a sense. So they don't grow as large as how it grew for northward IMF cases. You can expect them to grow as large as the boundary layer itself, where there are no parallel magnetic fields present, and it is still going to transport all these boundary layer ions into your central plasma sheet. In the event, if your magnetic fields are too strong and they are going to diffuse into a little bit into the boundary layer too, it is possible for KHIs to still operate exclusively on this inner edge of the boundary layer and still transport these inner edge ions into your central plasma sheet. So once these particles go into your central plasma sheet, they kind of convect earthward and make their way into radiation belts in your plasma sphere and it's into your inner magnetosphere system, which kind of drive a lot of these inner magnetosphere dynamics that can kind of dampen your satellite trajectories and so on. So one way or the other, whatever your IMF orientation is, it's possible for your deflected solar wind to make its way into the central plasma sheet. For cases like southward IMF, because the orientation is very favorable for reconnection to take place in the day side, you have much higher energetic electrons that can stream easily down these field lines and give us these great auroral shows that we see. So next time there's a major solar storm coming up, don't just look at the speed, also look at the magnetic field orientation. Yeah. All right.
Had to run out and get a new beer. There were so many. Um, Reminder everyone to please text in your questions if you have any. We'll start out with, how do we measure all of the different parameters of the solar wind?
We have dedicated instruments for that. So to measure magnetic fields, we have instruments called magnetometers that can measure your background magnetic fields. And ion analyzers can kind of measure what is the density, speed, and temperature of your solar wind parameters. And from all of these measurements, we can derive additional data products like what is your plasma pressure and so on. So we have dedicated instruments that kind of monitor your solar wind at all times, and they kind of give us real-time information about what is going out there in space.
What do 3D KHIs look like?
What?
A three-dimensional KHI. What would that look like?
So three-dimensional KHIs are kind of tricky because, I would say it would look like the same structure, but so imagine these boundary layers to go a little bit up and little bit down. So these kind of structures, it'll be like a cylindrical roll-up. So that's what I have seen in the simulations some of the folks have presented. And you need to know that, over here, these magnetic field lines are kind of tied to this plasma population over here. And when these vortices twist and bend or redirect the flow of plasma over there. The magnetic field lines, as I mentioned before, they are kind of linked to these particles, so they also get twisted and bent. And this kind of drives up a whole lot of plasma waves within this, which can kind of also heat the plasma. And that is why your magnetosphere is kind of like 50 times hotter than this solar wind, even though solar wind comes all the way from the sun.
Interesting. Do we have a good understanding of how turbulent the solar wind is as it approaches the Earth?
How turbulent the solar wind is. That's a question for a heliophysicist. I am not really sure about how turbulent these solar wind structures are, because while I do say that your IMF orientation keeps changing over time, these changes, I have seen them take place over a couple of minutes and also over a couple of hours. Sometimes they do tend to be steady over long periods of time, and sometimes they kind of fluctuate rapidly within very short intervals too. So I'm not really sure about how do you measure or study turbulence in solar wind. I know folks do that, but I don't.
In the IMF, when you talk about the hot IMF, what does that mean? Well, quantitatively, I guess, compared to cold.
Okay, so I think it comes down to the temperature, or the how energetic these ions are. So we usually refer to the magnetosheath ions as cold, because it's about 50 times less energetic than what you see over here within this inner magnetosphere. So this magnetosphere is heated up because of all this boundary layer processes and the reconnection processes that operate down the tail. But I don't remember the exact values of how much each of these regions typically average at. Yeah. But 50 is roughly where they kind of vary.
Okay, very interesting. I think that's about it. If nobody else has any last minute ones that they want to throw out to the line. No? All right. Thank our speaker once again. Thank you, Dinesh. Doctor. Okay, we're going to go. I don't know why he puts 5 to 10. We need a 10-minute break. So we're having a 10-minute break, so we'll reconvene at 7:45. And let's thank Lee once again for sending beautiful No? Damn it, Sam. Let's thank... Did anybody in this room send this photo? Well, but point is, all right, we'll thank whoever this is when we find out who it is. Enjoy it. And if you have any cool photos, please send them to samuelharthelio@gmail.com. And when you send your photo, please complain that he's not going to credit you. Okay, everybody, let's settle back in.
Got the long mic.
I think we may be back in business with the roaming mic, so I can roam about. So Cindy will get to roll about. Speaking of, it is time to introduce our. Oh wait. That's right. I forget. Astronomy in the news. Usually I do the first one, so this is weird. But wait a minute. Where's our man? There he is. He's walking in right now. The incomparable Dr. Caleb Gimar for Astronomy in the News.
Okay, all right. Okay, well, good evening, everyone. And here is our latest edition of Astronomy in the News. So I'll go ahead and begin. By the way, NASA is open for business now, everyone. Yeah. Yeah, so anyway, there will be plenty of news this month as opposed to last month. So first off, the skies of December. So this is the way the sky will look like without, of course, all the markers and stuff. If you go outside at about 8:30 p.m., about mid-month, you are in the latter part of autumn. Even though it's getting cold, winter does not officially start until the 21st of December, so you still have, for the most part, an autumn time sky to look at in the evening. So if you look right above you, you will still find that great square of Pegasus, the magnificent winged horse there. That makes up most of Pegasus's body. The mane on out to the head goes this way. The front two legs go this direction. And the Princess Andromeda is this kind of sideways A shape right here. And her mother, the very distinct W-shaped constellation Cassiopeia, the Queen. That W shape makes her throne in the sky. Now, you still have a little bit of the summertime sky left. Take a look over there toward the western horizon, and you will find the summer triangle formation, Vega, Deneb, and Altair. Each of these stars is part of its own individual constellation. Note the constellation of Cygnus, the swan, right here. That is home to an asterism called the Northern Cross. There's a crossbar, there's a vertical. And as we go on through the winter season, these constellations and the stars within them will start to move closer and closer to the western horizon, to the point that the Northern Cross will be standing more toward the western horizon at sunset by the end of the month. Nonetheless, over in the east, we do have the wintertime sky starting to appear. The mighty hunter Orion, best marked by the three bright belt stars there. The bright star Betelgeuse in one shoulder, the bright star Rigel down there in the foot. That constellation is rising toward the east. Make sure if you have a pair of binoculars, look around these constellations in a few specific areas, and you will find some of the easiest to see deep sky objects. You will find in the constellation of Andromeda, the Andromeda Galaxy, M31, right there. Just look for that cross of the sideways A shape. Look up a little bit with binoculars. You'll see a little gray disk of light there. That is the nearest galaxy to our own galaxy that is similar to our own galaxy, the Andromeda Galaxy. Look over here in the constellation of Taurus the Bull, and you'll find this little glittery patch of stars. That is the Seven Sisters, the Pleiades. Probably the easiest to find open star cluster in the nighttime sky. Very beautiful object. And then, of course, if you look toward Orion, look right below the belt and the sword region there. In a pair of binoculars, you will see kind of a gray glowing object with a few stars within it. That is the Orion Nebula. So it is a great time to use binoculars to see the deep sky sights. Now, we do have a couple of planets that steal the show right now. Saturn is still very well placed in the sky. If you look at it with a small backyard telescope right now, you will see the rings as just this little thin line through Saturn. It actually was oriented such that it almost was invisible. Those rings were almost invisible. Toward the end of last month, we are now starting to move around the sun, and Saturn is in such a way that those rings are becoming more inclined to us once again. So as the weeks go on and you look at Saturn, you'll see those rings become a lot more tilted towards us. And then Jupiter, right there, is rising in the east. It will be a very, very bright star-like object. You can't miss it. Look at it through a telescope. You will at least see a few of the 4 largest moons around it: Ganymede, Callisto, Io, and Europa. And then there is a nice meteor shower this month. So go out to a location that has an extremely dark nighttime sky, and you will see the Geminid meteor shower peaking at the middle of the month, around the 13th, 14th. Fortunately, we have a waning crescent moon that weekend, so the moon shouldn't be too much of a problem, and we might be in for a good show. That Geminid meteor shower is actually caused by the dust left over from the asteroid Phaeton as it's going around the sun. So what you're seeing is the fragments of this asteroid entering our atmosphere as that meteor shower. Probably about a meteor per minute, maybe a few more. We'll see what happens. So for the news part, Escapade. That is a couple of Mars probes. There are a couple of Mars probes, I should say, launched in the middle of the month. It is the second launch for Blue Origin's New Glenn spacecraft. Very capable booster. Again, went by really very well, and this time they actually landed the booster for this one back on their barge out at sea. So really fascinating stuff there. And these...
Essentially, we found that the supercritical water ocean could at least explain those carbon observations. But we didn't look at ammonia. So why do we even care about ammonia if it's not detected, right? Ammonia is proposed to be a key observable that could distinguish between different interior or surface conditions. We believe that you're going to get different abundances based on whether you have a magma ocean or a liquid water ocean, or if you have a shallow atmosphere or a deep atmosphere. But the thing is, predicting how much ammonia there should be is really hard. The first problem is we don't know how much nitrogen a planet has. So molecular nitrogen, or N2, it really doesn't show up in observations even if it's there. So it's hard to tell how much nitrogen is available to make ammonia. And then ammonia also dissolves in silicate magma and in liquid water. So if you have these environments, they could be keeping ammonia out of the upper atmosphere where we would observe it. So for my research, I wanted to see if I could tackle a bunch of different processes that could be depleting ammonia, and then see if that supercritical water ocean case is still possible. So my first question, will slow atmospheric mixing deplete ammonia? Essentially, that just means that your molecules are moving very slowly through your atmosphere. And when that happens, if we start off deep in the atmosphere, it's going to be much hotter. So here, chemical reactions happen very quickly, and they will dominate. So ammonia is just going to be destroyed to form N2. And as we go higher in the atmosphere, we're going to destroy more ammonia, get more N2. But as we're going higher, it's going to get colder. At some point, those reactions are going to be slow enough that atmospheric mixing takes over. So now our reactions have stopped. We've stayed at the same abundance. And now our ammonia molecules are just being lofted up into the atmosphere. And as we're going higher, we're going to be more susceptible to radiation. So photons are going to collide with your remaining molecules, and then we're going to destroy more ammonia. So I want to see if this process could be happening to match those observations. So here I have ammonia mixing ratios. That's essentially the fraction of ammonia that's in the atmosphere. And then I have pressure on the y-axis. And each of these different curves has a different strength of the atmospheric mixing. Essentially, I'm looking for, can any of these blue curves match that red data point? And you can see that none of them do, even though it's not shown here, but as slow as I make this atmosphere, it just can't meet the observation. So this process probably isn't an adequate explanation. My next question is how much ammonia dissolves in liquid water clouds? So essentially, I just use combination of Rayleigh distillation, Henry's law, ideal gas law, to figure out how much gaseous ammonia might exist below this cloud, and then I calculate how much it dissolves per layer. And then we see how much ammonia survives. So here I have percent difference in ammonia mixing ratio for 4 different cases. These cases have different reflectivities. Essentially, the higher the reflectivity, the thicker your cloud's going to be. So you can see that even if I make my cloud thicker, there is really not a difference in the ammonia mixing ratio. So this tells us that maybe these cloud layers, they don't matter very much. They don't influence the ammonia abundance. That actually makes things a lot easier. So now we can take a look at the supercritical water ocean. Oh my goodness, it's so compressed. So essentially, I use a geochemical model. And first, I want to calculate the aqueous ammonia to H2. Think of it as how much ammonia is dissolved in the ocean. Y'all got a drink there. Anyway, so I calculate how much is dissolved in the ocean. And then I can calculate how much ammonia would be in the atmosphere above that ocean, right where the atmosphere-cloud interface is. And we've learned that the clouds don't matter very much, so we can compare this to the observation. To do this calculation, I also need a number for how much nitrogen there could be. And since we don't really know, I just kind of explored 2 extremes. The first one is the minimum nitrogen that meteorites can accrete, and the next one is the maximum that comets can have. But the cometary value was too high, I realized, so I'm just going to look at the meteorite value. Okay, so here we have aqueous ammonia H2. Remember, that is the amount of ammonia dissolved. So I have that ratio on the y-axis, temperature on the x-axis. These different subplots represent different amounts of water that could exist in the interior. I have different curves representing different pressures. And since we don't have a surface pressure, so to speak, this just resembles where chemical equilibrium might occur in the interior. And so once I've calculated this, then I can calculate the gaseous ammonia to H2. And so this black dashed line is the observational constraint, and then this gray region is the region of error, also posed by the observations. Essentially, I'm looking for where do these curves dip into this gray region. That's going to tell us where our supercritical ocean case is possible. So at this point, I've already realized that 5 and 10 kilobar aren't going to work for the observations. So now we're going to focus on 1 kilobar. Previous work looking at the carbon species tell me that a temperature of about 680 to 900 Kelvin could work. So that's the temperature range I'm going to look at. So if we look there, we can kind of make it work, like right up there. That tells us we need lower nitrogen, but I mean, lower nitrogen is possible. So at the very least, it's actually not ruled out, even though our conditions might be a little bit narrower than we would like. But it's still very much a possibility. So it could be a supercritical water ocean. Is it habitable? Probably not. I don't think we could live in 680 Kelvin environment. But if there's some alien that can, that's fantastic. We just don't know what they look like yet. But even if it doesn't have life, this could be a new kind of global hydrothermal environment that doesn't need hydrothermal vents to drive it. You essentially have this planetary scale layer of hot aqueous fluids swirling around. It's nothing like we've ever seen before. So even then, it's still a really exciting environment to explore. Goodness, okay. Well, to conclude, slow atmospheric mixing is probably not enough to deplete the ammonia. K218b could indeed have a supercritical water ocean. We just need really, really low amounts of nitrogen, and our ocean probably equilibrates around 1 kilobar. And so even if K218b isn't a supercritical water ocean, we can explore that scenario for other sub-Neptunes and then explore more of that cloud chemistry to link that upper atmosphere to their surface conditions. Thank you. See, I was nice with the drinking water.
All right, thank you. How common are sub-Neptunes?
How common? Out of the 6,000 exoplanets, they're going to be closer to 4,000 out of the 6,000 exoplanets.
Very cool, thank you. Why are sub-Neptune planets so common compared to the super big ones?
The answer is we don't know. And that's part of what makes them so interesting. Because if we can figure out what makes them tick, then we can figure out basically what's happening with the majority of the exoplanets that we've detected. So that has yet to be discovered.
All right, someone asked about the implications of widespread fungi. Fungi, you put fungus, there's multiple, so it's fungi, on nitrogen concentration.
The implications of widespread fungi on nitrogen concentration. There's so much fungi that exists. I have no idea, to be honest. Whatever impact there is, that's something I'll have to look into. But I don't know what kind of fungi might exist out there, or if they. They're part of the nitrogen cycle. I'm not too sure.
What does it mean to have a non-detection?
Okay. So when we're looking at the transmission spectrum, we know what molecules are causing the absorption features because we can measure that here on Earth. Like no matter where you are, these molecules are going to make the exact same absorption features. So if we're looking at a certain wavelength range, and we know that certain molecules will be absorbing there, then if we don't see it in the observation, that tells us that it probably doesn't exist in the atmosphere to begin with, because we would expect to see something if it were there. And so we can constrain that, just how like little of it there could be, like maybe it's possible it's contributing a little bit, but we know like if there was a lot of it, then there would be much more evidence that is there, basically.
Very interesting. What about global algae or bacteria?
What about them?
For methane production.
For methane production? So the work that has been explored was, what if this planet had 50% of the methane producing bacteria that Earth had, and that led to maybe like 1% methane. So I'm not sure I'm convinced that like if they had like 100% of Earth's bacteria, that we could get up to 10% of the atmosphere, but it can contribute a decent amount if we do have that much bacteria in the ocean.
All right. The last question is, what informs the predictions of these different exoplanets? How can we be sure that what we're seeing is what's there?
You know, the fun thing about being a theorist is that no one can like prove me wrong for like 100 years. So if you ask me if I'm like sure that something exists, I don't. I'm leaving it up to the next generation to figure it out. I'm just providing the tools for other people to have the evidence. But what informs the predictions? Essentially, when we do our models, we get a good idea of like the abundances that we could have, and we just need like really precise observations to rule things out. Because we might say like, okay, a magma ocean, that's gonna have like 10% carbon monoxide ish, and then we're seeing observations that are like, okay, it could be like somewhere around, it'll be like less than 20%, so it could be possible. In reality, there could be like nothing, you know? So it really just is down to the precision of the observations. The more precise we can make them, we can see what models agree the most, essentially.
Very cool. All right. And lastly, Aaron would like to issue a profuse apology, but as I told Aaron, we'll just blame Sam since he's not here. Let's thank Cindy once again. All right. Hey, so for those of you that can't stick around, I really want to thank you for joining us once again tonight. Had a great time. A reminder, we will not see you in January. We never do one in the new year, and we're going to continue that. But we'll see you again in February, that first Wednesday. I don't know what date that is, but do you know? We won't say the 3rd because we don't know what it is. It's the 4th. There we go, February 4th. But for those of you that can stay around for trivia, we'll start in about 5-ish minutes, so around 8:30-ish. We'll come around with the sheets and pens if you need them. And reminder, groups of 4 maximum. No cell phones allowed. And think of your cleverest team names you can. Thank you. Is everybody ready? You got sheets and pens. Thank you. Yeah. All right. Let's go.
Donde está el clicker? Question 1. Cosmology. Right. Cosmology, or the study of the origin of the universe, stems from the Greek word, or cosmos, meaning what? A, purpose, B, sky, C, heaven, or D, order. All right, let's see. That's Kausuoxi. We can read Greek. It's just hard. Yeah. It's Kausuoxi. Something like that. Oh, Cosmos. Well, that's anticlimactic. Cos. Oh. Xi. Um. Cosmotomology.
Question 2. Good grief. I didn't order one. In the popular sandbox video game Minecraft, how long is the day-night cycle? Is it A, 10 minutes, 10 minutes, B, 11 minutes, 9 minutes, C, 12 minutes, 8 minutes, or D, 12 minutes, 10 minutes? The most recent. What?
Yeah, wait.
Vanilla.
Wait, does the day-night cycle change in each patch? Or from patch to patch? We'll go with vanilla. And fear not, if you need a question repeated, we will come back. All right, everybody got their guess? Question 3. I-Atlas. The 3 in 3 I-Atlas denotes it is the third interstellar object discovered. The first interstellar object discovered was 11 Oumuamua with a trajectory. Oh, one eye, my bad. One eye Oumuamua with a trajectory suggesting it came from which star system? Oh, you only got 3 answers. You got a third of a chance. A, Altair, B, Vega, or C, Deneb. You got to. I mean. It's the third eye. It's right here. That's Avi Loeb's. Yeah, that's his reasoning for. Huh? Oh no. The worst part about Avi Loeb is that he works at Harvard. That's the worst part.
Literally.
Not Avi Loeb.
Wasn't it? Wasn't All right. Question 4, which is about at this time of day in this part of the country, the iconic green color of aurora borealis arises from the interaction between an energetic particle and what element in Earth's atmosphere? Is it A, hydrogen, B, carbon, C, nitrogen, or D, oxygen?
Okay, Simon has a. I know mentally what you're thinking, but this is also a memory recall because Dinesh quite literally put up a graphic showing. So, and he kind of talked it out. I think he talked out like the red and what happens and. I shall say no more. Oh, yes, but the graphic was graphic.
Nobody knows is the real answer. All right, question 5. Oleg Kononenko holds the record for the most time spent in space, having 5 extended missions on board the International Space Station. How many total days has he spent in space? Is it A, between 300 and 400, B, between 700 and 800, or C, between 1100 and 1200, and lastly D between 1500 and 1600.
Sam, if you're watching or listening, what? Why would you not just give the days? Why give a range? Like, is it unknown?
It's time. Well, you know how it goes. I mean, Oleg Kononenko from Russia.
No, yours. Oh,
Wait,
we switched.
that keeps happening.
All right. Question 6. Like hot water, but hotter. This image shows a moss-covered expanse over the Eldron lava field located in which country? A. Iceland, B. Mongolia, C. Hawaii, or D. Madagascar?
Sam, Hawaii is a state in the country of the U.S., so I'm not sure what he was thinking of here. Okay.
Everybody got an answer? All right, bonus. We'll go back. Bonus, in the bonus section, because that's where the bonus goes. Who among these men is the greatest physicist? All right. The answer with the most votes is awarded 1 point. Anyone who effectively argues a fourth individual may also receive credit. Is it A, Albert Einstein, B, Galileo Galilei, or C, Isaac Newton? Once again, a prisoner's dilemma. All right. If you have questions, let me know. Does anybody need a question repeated? Hold your fingers up. Minecraft. Minecraft, not Mein Kampf. It's a meme. It's a video. No. Chicken jockey. Well, we're not making money.
I do have to say that Jack Black was a goat for that. That was what a. Yeah. What wasn't he in the Mario one also? Yeah.
I don't know about Jumanji. I don't know about Jumanji. Yes. Yes.
All right. Another one besides two? Anybody? Anybody?
Oh,
Four, five? No? All right. What?
which question?
Huh? What? Oh. Okay. All right. Well, as always, if you are all done, please bring up your sheets and your pens. How did we do? Only two?
Is that ours?
Oh, wait.
Is that Publix?
What the hell?
Is that?
It's Nate.
Oh, Nate.
I don't know who that is. It's Bic.
Oh, big.
Prevagor.
I saw the P and I was
That
like,
sounds like a anti parasite medicine. Prevagor. But like a I don't know. Like
all right, we'll take a quick break to grade and then we will come back with the answers. Um, I'm trying to. I want to. Kyle, you have terrible handwriting. You have terrible handwriting.
No.
It's not that bad.
No one else.
The next lowest was 1.
All right. Let's get to the answers. For question 1.
Yahoo! Oh, Sam's in choir practice. Cosmetology. Order. That was my second guess. I don't know why. Yeah, but the damn Greeks.
All right. I'm happy I knew this one. The Minecraft, it's a perfect even cycle, 10 minutes, 10 minutes. And one way, if you've ever played it, notice the sun and the moon are always perfectly opposite from each other, which means it has to be they have to be perfectly synced as far as the times go.
That's the weirdest part for you? That's the weirdest part?
You know, when the moon comes out, you got all the zombies, the skeletons, the spiders, the creepers. Yeah. Yeah. Well, I mean, you walk endlessly, so you never know.
Someone apparently did reach the end.
And there is the end.
There is the end, the nether world. Question 3, Atlas. Name that star system. Vega. Pure guess.
Damn it, I knew it.
Yeah. That's what. Simon's gonna have a fit. Well, maybe not. I don't know.
I'm going to have a fit on this next one because it was 50-50. The Aurora Borealis. What makes it green? It is oxygen. It is indeed oxygen. Oxygen has a green line at 636 nanometers.
That's red.
Wait a minute. 577 nanometers. There are two lines. I was thinking of the red. But yes, there's the 577 and 636. So that's why you get green and red aurora, because oxygen is versatile.
Yeah. Sam, if you're listening, we want to name that Pokemon of Aurora. All right. This next question deserves an explanation from Caleb. How long was he in space? A long time. 3 years worth. I want to know why it's a range.
So, if you know how long the general tour of duty is for an astronaut on board the space station, you can figure this out. The astronauts usually stay on a space station for about a 6-month tour. So 6 months, 6 times roughly 30 days, 180 days. 5 years, 5 times 180, that's about 900. Add a little change to it, you get the right answer. Yes. Because some of the stays are just slightly longer than others, and then I'd have to look at his history. He might have been up there during a time when they had some weird thing happen where they had to delay flights or something like that, so, yeah.
That's not a range.
Well, again, I think Sam was just being kind and figuring it. Yeah. Well, well, he could have just made. He could have made like 3 really close numbers or something, and then it really would have been. This one, you can at least, if you know generally, you can do the math and figure out the answers. So I mean, but here, I'll give this back to you.
Thank you, Caleb. That elucidates it for us. And yes, once again, samuelharthelio@gmail.com for your beautiful pictures and complaints. All right. Speaking of beautiful pictures, that lava flow region is on the island of Iceland. The island country of Iceland. How many of you knew that? Because let me tell you, it doesn't look like Iceland. And now I want to go. I've already wanted to go to Iceland, but now I really want to go to Iceland. No, but I know it's green, but I always was told that Iceland was taller than this. This seems quite flat. What? What? Oh, crap. Yeah. All right, yeah.
It obviously wasn't Hawaii. All right, so for the bonus,
So most of you voted for the lovely Isaac Newton. We had one lovely honorable mention of our very own Rob Ebert. No other write-ins. There was a Kepler mention? I didn't see one in there. Oh, well, I didn't read your explanations unless it mattered, so.
yeah, Prisoner's Dilemma, it was Isaac Newton. Oh, I agree. Yeah. He had the 3 laws. I used those. I used one of those laws in my research. Oh, I said Galileo Galilei. But what? Oh, well, the Paul Dirac. That was my first thought, and then also Wolfgang Pauli and Werner Heisenberg.
I thought Werner Heisenberg was an acceptable one as well because of uncertainty. But none of y'all. Okay, whatever. But my other one was Einstein because actually, fun story about Einstein. He used to vacation, or he used to have a house in the same area where my family has a house on Long Island. So it's just a fun connection that, I've sort of lived next to where Einstein used to live. that's just pretty fun, you know? That's pretty fun. And yeah, okay. So honorable mention tonight is you all there, whatever your team name was. You did good. Rob Ebert was a fun choice, but you didn't win. All right. Third place tonight, which is getting a nice tiny little poster of Kepler 16b and some cool stickers, is Jesus Rice. Ah, Jesus. All right. In second place, which will get each team member will get these cool, and Michael, you may recognize these because you donated them to us. Storms from the Sun, upside down. Which kind of goes with Dinesh's talk tonight. The Star Masters. And there's only 2 of them, so, you know. What was I going to say? Spread those posters out, please. Get rid of them. Don't give them back to us. All right. And in first place tonight, which we'll be getting, each team member will get one of these beautiful Super Earth HD 4037. No. These are terrible numbers. 4307. Thank you. 4307. G, which means it's the star is A, the first planet's B, C. So this is B, C, D, E, F, G. It's the 6th planet. It's the 6th planet of this system. Congratulations to this team for getting all 6 questions right. Also, we haven't seen that in a while, except for the bonus, but that's not. I don't count that. And I love your name because it's Sam's fault. Sam's fault. There you go.
Thank you very much.
All right. It is indeed Sam's fault. And we have indeed reached the end of our program. It says February ? But we've solidified it as February 4th. That is when we will see you next. We thank you all for coming. We thank the Blue Star once again for hosting us as they do every month. And we will see you all in February. Happy New Year, Merry Christmas, and all of the holidays.